Okay, friends. So we are going to learn the finite difference method for analyzing the plates. In the past, we have learned some methods, for example, Navier's method, Fourier series method, Levy's method. These are analytical methods and it has some limitations. So there must be some numerical methods such as finite difference method should also be known to us for solving the plate problems. So, finite difference expressions may be obtained from the definition of the first derivative with respect to x of a continuous function, which is shown here. It can be given by dy by dx is equal to limit delta x tends to 0 yn plus 1 minus yn divided by delta x. This is a standard definition of the differentiation and which is the first order. Now we can also write this approximately as dy by dx is equal to approximately delta yn by h, where h is the difference between two intervals yn plus 1 minus yn divided by h. Here the subscript n denotes any arbitrary point on the curve, and over an increment delta x can be written as h. As I told you, it is the interval between the two function values, and this can be written in an approximated form. Now this is also called as first forward differentiation. Now why forward differentiation? Because we know that if function value is on when x is equal to center point xn, the function value is yn, and the forward value of yn is yn plus 1, and the difference of these two, because we have taken one point forward, this is also called as first forward difference of y at point xn, and this can be written like this. Now what is first backward difference? If I take the differentiation of a function and take the difference with the one value backward, for example, in this curve you can see here the one value backward is yn minus 1 and the forward value is yn plus 1, and this is a function value at x equal to xn, the function value yn. So what do you mean by first backward difference? When you take the difference with the backward value yn minus 1, and that is called as first backward difference. Now similarly we can also write the central difference equation which contain the nodal point symmetrically located with respect to x. So it is very easy to write the central difference equations if we take the central point as xn. So the right hand side value function and the left hand side take the difference of that, that is if function value at xn is yn, it is a symmetric point, so the right hand side value yn plus 1 minus yn minus 1 divided by 2, this is called as central difference equation. Now we have seen these three types of equation. All three are correct, all three can be used, but we will throw some light which one is more accurate and which will give you more improved results. So we have seen three types: second forward difference, second central difference, and second backward difference. If you try to take the differentiation, this expression written because of this quantity depend on the value. See, we can evaluate these values actually for its second derivatives. So if we take the second forward differential equation and second central differential equation, we come to know that these values actually depend on the values of the function two intervals ahead and two intervals behind the point under consideration. That is point, what is the point under consideration? It is x n and function value is y n. So this, if we take the further differentiation of this, of the second forward difference and second central difference and second backward difference, we come to know that we will see in the next slide that why it is so. To improve the approximation, the second difference is expressed in terms of the function only one interval ahead of and behind the point, and to do this for further differentiation we write this equation. This is backward differentiation, this is forward differentiation, and even the vice versa, both can give us again the second differential equation. So in our cases, for better approximation, we are going to use this kind of second central differential equations, and the reason I told you, which I will show in the next slide, that why it is so. So now first differentiation of three central, forward and backward we have written. We are now talking about second differentiation, that is d square y by dx square. So it can be written either of three ways. One is forward difference equation, that is delta y n inverted, this is invert symbol, delta y n backward difference 2 times, this is also 2 times, we give you the difference equations forward and backward, and then delta square y n when we are considering the symmetry point x n, and we write the one value ahead, one value behind. So in all three cases, if you try to follow this, you can write in terms of forward difference yn plus 1 minus yn, here in the backward difference equation yn minus 1, and central difference equation you can write yn plus 1 minus yn minus 1. Now we go further, you can see this operator of delta forward difference, here you can see the inverted operator of delta for backward difference, and here you can see the delta for the central difference. Now if you write this equation according to, these are the function values, and according to our formulas, you can see the forward difference give you, you can write delta yn plus 1 again. This is for the forward difference. What is the forward value of delta yn plus 1? It is yn plus 2. So difference of yn plus 2 and minus yn plus 1. Similarly, the forward difference of yn can be written as yn plus 1 minus yn, and finally we got yn plus 2 minus 2 yn plus 1 yn. Here we are getting similar approach, we are getting yn minus 2 yn minus 1 plus yn minus 2, and here we are getting yn plus 2 minus 2 yn plus n minus 2. So you can see in all three cases the original value is function value is yn, but you can see the n plus 1, n plus 2, two values behind, and forward, and here two values behind, and here also two values behind and forward. So these equations are not, we are not going to use, this is just for your explanation. What I explained to you is we are going to use the equation is this. So one forward and the backward of the function value yn, difference of that will give you delta square. Now we expand this and we will see what will happen. So here you can see that by expanding this, because this is the backward differentiation, that is yn minus 1, and again we are operating on the forward equation on both of these values, delta yn minus delta yn minus 1, and you can write the forward values delta yn as yn plus 1 minus yn, forward values of yn minus 1 is yn minus yn minus 1, and after simplification we get yn plus 1 minus 2yn plus yn minus 1. So you can see here just yn is one value and one value ahead and one value behind, and this will better give us better results, better approximation. And this is, I would say, nothing but again the central second order differential equation can be expressed. Now in the beginning I was about to mention that what is the use of these approximate methods, because in plate theory we are going to have the fourth order differential equation and analytical solution is very difficult to get. So these expressions we are going to replace it with the difference equations, and finally those governing differential equations are to be converted into algebraic equation, because now we have seen that you can see this second order differential equation can be replaced with simply the algebraic equation. This is nothing but algebraic equation, yn plus 1 minus y2 and yn plus yn minus 1. So our all final equations will be converted into algebraic equations, and simultaneous algebraic equations are easier to solve rather than the complex differential equation, and that is how this method is for. Now similarly we can also write the third and fourth central different equations by following the previous formulas for the second central differential equation, that is delta cube yn, delta you can take it in bracket delta square y, this is known to us, so this value is known to us, and then we again operate the central difference equation on this, and that when we expand this on the central differential operator we can finally get this value for the third order central difference equation, because in plate theory we have to write equation for fourth order, so we have to go up to fourth order. This is for the third order, so the fourth order can be written again. You can operate second difference equation on the central difference equation, and from the known equations you again operate on second difference equation. So it is easy to carry out from our previous formula. It is easy to write this from our previous formula. We have expanded this, simplified further, and we get this. So in the process we are able to write the fourth order equation. Now in case of plate our w is a function, let's say it is a deflection, but it is again a function of x and y. So if we consider for example the rectangular plate, and by taking basically the grid which I have shown in my previous slide, we can divide the plate into a grid like this. So in rectangular plate we can divide this and assume that these two grids are same, of same size, that is the square. This grid is square, this is height h and this is height h. So we are